Welcome back, everybody. In this video, I'm going to be going over some of the arguments for using concentricity on an engineering drawing. So there are none. Thanks for tuning in. I'm going to have another video coming out soon. Have a good one. Okay, I'm kidding. There's three common arguments that I've heard. One is that it's good for high precision parts. The second is that it's good for controlling thin wall parts. And the third is that it's good for controlling rotating shafts. Before we get into the arguments for it and against it, let's look at the definition. So concentricity is defined as the condition where the median points of all diametrically opposed elements of a surface of revolution are congruent with a datum axis. So what does this mean? And you can look at figure 7-16 in the 2009 standard for a pretty good image of this. Basically what it means is that if you've got a datum feature and a feature of interest, you will take the datum feature axis and extend it through the feature of interest, and you will draw a cylindrical tolerant zone around that datum axis. You will then take a line and put it through the datum axis perpendicular and find the point where it pierces the surface on either side. And you will take the points on either side of the datum axis and find the midpoint. And if that midpoint is within the cylindrical tolerant zone surrounding the datum feature axis, then your part is in spec. And this is a 2D representation, but of course you do it in 3 dimensions. Argument 1 is that concentricity is good for high precision parts. And I don't like this argument because one control is not more precise than another. We have one set of geometric controls, and we don't split them into high precision and low precision geometric controls. We should be using our geometric controls based off of the function of the feature in the part as well as the greater assembly. So I don't like this argument at all. Argument 2 is that it's good for controlling thin wall parts, and this one's pretty easily dismissed because it's significantly worse than using a position tolerance, and I'll show you why. But the main reason is because material modifiers cannot be used. So let's see an example where we have let's say it's a pressure vessel with a 7mm minimum wall thickness. So if we were to use concentricity, that means we have to look at the size tolerance and the concentricity tolerance and figure out some balance where we'll never violate that thin wall condition. So in this case, we say that the LMC size is 15mm, and if it's perfectly centered on the outer diameter, that means we've got a wall thickness of 7.5mm. And if we use up that entire 1mm concentricity tolerant zone, we get our thin wall condition of 7mm. Now, if we look at the maximum material condition of that inner diameter, it's 14.5mm. And if it's perfectly centered, we have a wall thickness of 7.75mm. But if we use our entire concentricity tolerant zone, it comes down to only 7.25mm. Which means that we're not using that entire outer boundary that we should be allowed to. Whereas if we use a position tolerant zone with 0 at LMC, that means we can use a larger size tolerance, and we can actually get more locational tolerance as well. So our LMC size in this case is 16mm, which when it's perfectly centered on the outer diameter gives us our thin wall condition of 7mm. And as that inner diameter goes from its LMC size, which is the largest hole, towards its MMC size, which is the smallest hole, we gain positional tolerance in the form of bonus tolerance, which allows us to get up to 1.5mm of positional tolerance. So the third argument, which I find is the easiest to defend but still falls apart under scrutiny, is that concentricity is good for rotating shafts. And this is because it's supposedly good at managing weight distribution. So let's look at an example and look at some different types of form errors and how it would register with a concentricity tolerant zone versus a positional tolerant zone. So the first one is 0 positional tolerance, 0 concentricity tolerance. The center of the shaft is just located nicely and there's no form error. But if we were to add some form error where we have a flat on either side, this would still register as 0 positional and 0 concentricity tolerance. Now, where concentricity might come in useful is if you were to have a flat on one side, this would be an unbalanced shaft, and it registers as a non-zero concentricity tolerance. So this is the argument for why concentricity is useful. But it kind of falls apart if you look at something like a trilobed feature, where this would still be a reasonably balanced shaft, and but it would still register as a non-zero concentricity tolerance zone. If you go a step further, and if you work with high-speed shafts, typically you'll get your shaft balanced. So you're not relying on the machining to balance a high-speed, high-precision shaft. The idea of using concentricity for rotating shafts because it's somehow better than positional or runout seems kind of silly. So in conclusion, it's not better for high-precision parts because concentricity is not inherently a more precise geometric control. It's certainly not better to control thin walls with. And for rotating shafts under scrutiny, the argument kind of falls apart because we typically will balance shafts that need to be balanced. So thanks for tuning in and watching. Hopefully this was a useful discussion on the geometric control of concentricity, and I hope you have a good one.